Hi, everyone. Thank you for inviting me to speak in the Group Actions on Hyperbolic Spaces section. What I'm going to talk about is joint work with Spencer Dowdle and Sam Taylor. In the first part of my talk, I'll tell you about stretch factors of free group automorphisms. And in the second part, I'll tell you about free bicyclic groups. So let's start with motivation for the first part. Let's start with a closed surface of genus G. And let's consider a pseudo-Nassau homeomorphism on this surface. So what is a pseudo-Nassau homeomorphism? It's a surface homeomorphism which comes with two invariant foliations, lambda plus and lambda minus. So locally, you see two invariant foliations. They can have singularities and a number lambda phi called the stretch factor, such that locally it stretches one of the foliations by lambda and it contracts the other transverse foliation by 1 over lambda. So lambda phi is called the geometric stretch factor. And then I can look at the map induced in homology by the surface homeomorphism. And I can take, that's a linear map, and I can take the spectral radius of that map. And that's called the homological stretch factor. In general, the homological stretch factor is always less than equal to the stretch factor. So then the question is, when are they equal? And this question was answered by Thurston and Band and Boylan. So if I have a pseudo-Nassau homeomorphism, the stretch factor and homological stretch factor are equal if and only if the invariant foliations of phi are transversely oriented. So in particular, what that means is there is no there is no odd trunk singularity. So let me draw a picture to explain what it means to not be transversely orientable. So let's say this is a foliation, and a transverse orientation on this would be something like this. And if so it has to be compatible. So, but then when I come all the way around the circle, it's not compatible anymore. So if there is an odd trunk singularity, the invariant foliation is not transversely orientable. And the theorem is that the geometric stretch factor is determined by the homological stretch factor if and only if the invariant foliation is transversely oriented. So there is a guiding question here in general. Can topological invariance of a surface homeomorphism be recovered from its homological data? In this particular case, when the foliation is oriented, then yes, the geometric stretch factor can be obtained from the homological stretch factor. But there can be more other invariants people might want to study. For this talk, we are interested in the stretch factor. Okay, so let's move on to the first result. So I want to consider free group automorphisms. So phi is a map from a free group to itself. It's a free group automorphism. In particular, I want to look at outer automorphisms. The group of outer automorphisms is basically the odd group quotiented out by the inner automorphisms. And the inner automorphisms are just conjugations. And not just any free group automorphism. In this talk, I want to look at something called a fully irreducible free group automorphism. These are automorphisms, no power of which preserves the conjugacy class of any proper free factor. So what's a free factor? If I write my free group as A star B, then both A and B are called free factors. So this is analogous to pseudo-Nassau in the sense that a pseudo-Nassau homeomorphism is one, no power of which preserves the homotopy class of any closed curve. So here are two examples. Here's a non-example and an example. So in the first case, I'm sending A to B and B to A, which means that this free factor AB is preserved because I can write my free group as the rank 2 subgroup free product C, And then under my automorphism, the AB subgroup is fixed. It's preserved. It's not fixed, but it's preserved. So this is not a fully reducible. This is not a fully reducible automorphism. Whereas in the second example, I claim that this is a fully reducible automorphism. These automorphisms are very mixing. They don't preserve any free factor. So now let's define analog of stretch factor and homological stretch factor for these free group automorphisms. So the stretch factor I want to define as the growth rate of conjugacy classes. So I'm taking conjugacy class in the free group, so some free group element. I apply big powers of phi and I count the word length with respect to some basis. And then I take this limit. And I take the supremum over all words in the free group. So let's look at an example. So let's look at this free group automorphism, which I said is fully reducible. And then let's pick W to be A. I keep applying phi to it, and then I count the word length, let's say in the basis ABC. So I have 1, 1, 1, 2, 3, and so on. And I want to know how is this growing. So one way to compute this growth rate is to use matrices. I can write a transition matrix for this automorphism, where A maps to B, then B maps to C, and C maps to CA. So I just keep track of where each element maps via this matrix. And then I think of the 1, 0, 0 vector as the vector corresponding to the element A. So now if I look at m to the n applied to this vector VA, and this norm here is where I just add up all the entries of the row, then I'm actually getting the word length of my resulting nth iterate of A. So linear algebra can be used to compute this growth rate. And in fact, in this example, this growth rate would be the spectral radius of this matrix. So here, lambda phi is the spectral radius of M. So this is phi. So that's the geometric stretch factor. And then by looking at a map induced in homology, which again will be a linear map, I can also talk about the spectral radius of that map, and which I define to be the homological stretch factor. So for fully reducible automorphisms, the geometric stretch factor is always strictly greater than 1. And in general, the homological stretch factor is always less than or equal to the stretch factor, which you can imagine because when we pass to homology, we're basically abelianizing. And when you abelianize, there might be cancellations happening. So we might be losing some information. We'll see an example in a little bit. Okay. So then the question now is, as with pseudo and Ossoff's, when are the geometric stretch factor and homological stretch factors equal for a fully reducible automorphism? So this is the first question we answer in joint work with Spencer Dowdell and Sam Taylor. So if you start with a fully reducible outer automorphism, the following are equivalent. The stretch factors are equal if and only if the automorphism has an orientable graph map representative. So I'll tell you now what is a graph map representative of an automorphism, and then I'll tell you what it means for it to be orientable. And for those who maybe know some of this stuff, this is equivalent to some train track representative of phi being orientable. So stretch factor symmetry has something to do with orientable graph map representatives. Okay. So let's see what is a graph map representative of an outer automorphism. So I have this automorphism. A goes to B, B goes to C, C goes to CA. Well, I can write this graph of rank 3 where the edges are labeled by A, B, and C. And now I can view this map as the edge A maps to the edge B, the edge B maps to the edge C, and the edge C maps to the edge path, CA. So now I've viewed my automorphism as a graph map. Here's another example where the example is slightly more complicated. But again, I can just view this as a graph map on this rose with 4 petals. Now the edge D will go to the edge path A bar, D bar, C bar, and B bar. So there is a difference between these 2 graph maps. The first graph map is actually good. It's good from the perspective of computing growth rates of elements in the free group. When we iterate this graph map, we can use matrices because there are no cancellations happening. When I keep iterating C, there are no cancellations happening, and then I can use matrices to compute growth rates. Whereas in the second graph map, if I just keep applying my map, D goes somewhere, and then I apply phi again, then it goes somewhere, then I start seeing cancellation. So if I did the matrix computation, if I do this matrix computation, just by writing the matrix for the second graph map, the growth rate or the lengths of elements under phi will not be faithful because the matrix is not keeping track of these cancellations. So the growth rate is not computed correctly. So this is a bad graph map. And the good graph maps are exactly what train track graph maps. So the whole machinery of train track graph maps is to start with a bad graph map, but do some moves and get a good graph map. So then you can still study your automorphism by this like graph maps and linear algebra and so on. Okay, so I've told you what is a graph map representative of an automorphism. You can always write a graph map automorphism, whether it's good or not, and then you have to do some hard work. Now let's see what is a orientable graph map. What is an orientation on a graph map? Okay, so an orientation on a graph is a choice of orientation on each edge of the graph. And then we say that the graph map is positively orientable if there is an orientation on G such that each positive edge maps to a positive edge path. It's called negatively orientable if there exists an orientation on G such that positive edges now map to negative edge paths. And if it's either positively or negatively orientable, we say the graph map is orientable. If it's neither, then we say the graph map is not orientable. So let's look at examples. So here is an example of a positively orientable graph map. So I have some orientation on all edges, and the small letters A, B, and C mean those positively oriented edges. So now under my graph map, each of these edges, A, B, and C, are mapping only to the positive edge paths. In the second example, so the capital letters stand for the negative edge paths, the opposite orientation. Here, every edge is only seeing edges in the reverse orientation. So this is a negatively orientable graph map. And in the last example, A maps to B inverse C. So it's seeing both B and its inverse. So this map is not orientable. No matter what orientation I choose for these edges, I will always see B with both the orientations in the image of A. So the last map is not orientable. Cool. So now earlier I told you about stretch factors for free group automorphisms, but I can also define stretch factors for graph maps. And because I'm realizing free group automorphisms as graph maps, then these two definitions are actually going to be compatible. So let's start with a graph map. Then I can define a transition matrix for that graph map, where each entry is the number of times an edge crosses other edges in either direction, in any direction. So let's simultaneously do an example. So here, if I write the transition matrix A, so A crosses B, B crosses C, and C crosses A and C. And here I have A crosses C, so I don't care about in which direction it's crossing. I'm just going to count how many times it crosses. B crosses CA and C crosses CAB. And over here, A crosses A once, it crosses B twice because I don't care about which orientation. And it crosses C once, B crosses C once, and it crosses C crosses this. So these are the transition matrices associated to these graph maps. Now I can also like think of the map induced in homology for this. Like the graph map induces a map on corresponding homology. Or basically, if I abelianize my graph map roughly, then I can also write a different matrix where I cross how many times an edge crosses the other edges, maps over the other edges with orientation. So an example is best. So in this example, even if I abelianize things, so by abelianizing, I mean I don't care about which order things are happening. So in the first case, I will get the same matrix. In the second case, so now it will be like A maps to C with a negative orientation. So that will be like a -1. And everywhere there will be a minus sign. So M will be just -A. And in the last example is where we see the difference. So now because I care about orientations or I abelianize, once I abelianize, these B's will cancel out and A will just map to A and C. The rest stays the same. So we see that here, every entry of M is less than or equal to every entry of A, up to taking absolute values. Here, everything is positive, but M is smaller than A. So that's what I was writing here. The matrix M is smaller than the matrix A. And then I define the geometric stretch factor to be the spectral radius of A and homological stretch factor to be the spectral radius of M. And it's clear from this last example, or I guess in all three examples, that the homological stretch factor is less than or equal to the geometric stretch factor. Because when you quote unquote abelianize things, you like lose out some information. So before asking about stretch factor symmetry for free group automorphisms, let's just ask the question, if I give you a graph map, when are the two stretch factors equal? So that's the next result. If I have a graph map with a primitive transition matrix, so we need some condition on transition matrix A. Primitive means that some power of A is a positive matrix. Then these stretch factors are equal if and only if F is orientable. So when I say F is orientable, I mean F is either positively orientable or negatively orientable. And the intuition is clear from these examples, or at least one direction is clear, that if F is orientable, so if F is, let's say, positively orientable, then the matrices M and A are both equal. So of course they have the same spectral radius. For negatively orientable, M is negative A, but still the spectral radius, which is the absolute value of largest eigenvalue, is still, they are still equal. And clearly in the non-orientable case, they are not equal. But they need not be equal. So at least one direction is clear for this theorem. Okay, so connecting this back to our original question for free group automorphisms, we wanted to understand that if you have a, okay, so here's a theorem again. If I have a fully reducible outer automorphism, I wanted to understand when is the stretch factor determined by the homological stretch factor, or when are they equal? And they're equal when I can represent phi by a graph map when I can find a graph map representative, which is actually orientable. And we apply our, so for these automorphisms, the correct graph map representatives, like these train track representatives, do have primitive transition matrices. So that's why we can apply our graph theorem to get this theorem about fully reducible automorphisms. Okay, so this was the first part of my talk. And then now I'll tell you about the second part, which is about free bicyclic groups.